I decided to talk about hashing after all because it would be a shame if you don't know about more modern hashing. And the streaming model will be on next week. And also, I'm gonna try to upload the sample for midterm exam soon. And just note that the sample are from previous offering, which is it's a take-home exam. It was take-home exam, so it's gonna be a bit harder than this one. And some of the question is like from previous offering kind of is related to some topic that is that we not cover yet. So if you see some question that you feel it seem unrelated, then like just ignore that.
Yeah. Will we have access to a note sheet or anything like that?
I didn't finalize this yet, but I think you can get maybe like one sheet for your note, but you cannot use like a mobile phone and any other electronic helps. Yeah. Okay. Yeah.
What's the content cutoff for an exam?
Right. So basically, until next week. Yeah. Yeah. There can be like there's gonna be something about randomization for sure. Yeah. Okay. And good. So let me recall again, right? We see that ideal random function is good. It's easy to analyze, but it's sometimes inefficient. You cannot just assume that you have it in your algorithm. And so we just kind of try to come up with some function that behave like a random function instead. So let's recall what are the behavior of random function. One simple behavior is that it's uniform, right? Each element is mapped to some number with like a uniform probability. Next has small collision. That is two different elements mapped to the same place with small probability. And if it's the random function, this would be actually exactly 1 over m. But even if it's at most 1 over m, it's good too. This is what small collision property is. Pairwise independent. This is when you focus on two different elements, like two different key x and y, then they behave like independent event. That is the probability that this thing maps to I and this thing maps to j is just like 1 over m squared. So it behaves like independent event. Okay. And yeah, like ky is independent, the same thing like pairwise, but like for k keys. Okay. So this is like a kind of if it's n-wise, it implies k-wise, it implies 2-wise, and 2-wise imply both this, right? And like last time, I show you a hash, like a simple hash family, which certify this one, right? And that one is what? Do you recall? It's like something like this. Like if you say that x of a, where x of a map from u, like from some prime to some number m, this is just ax and then mod p and then mod m. And then the hash family is just contains all the A, all HA when A is in 1 to P minus 1. This is like a super simple hash family, and it satisfies this one. And does it satisfy this? Does it satisfy this one?
No.
No. Why?
Well, from last time, I think it always maps 0 to 0.
Yeah, thanks,
So it's
John.
uniform.
Yeah, so it doesn't satisfy uniformity. So it would mean that it doesn't satisfy any of these things. Yeah. So you can try to prove at home that if it is two-wise independent, it does imply this and this. But this one doesn't even satisfy uniformity, so it is not satisfy any of this. Yeah.
Can you explain again why it's important that we have like a whole family of functions as opposed to just one function that like does this behavior?
Right, because when we fix a function, like let's say it's like a fixed function, then we cannot even talk about probability. Right, it's nothing random about this. Like in order to talk about some probability, you need to say that okay, you have some families, and then you sample from that family. That's when you use some randomization, and now you can talk about some probabilistic guarantee. Make sense? Okay. So we see the example of this one, like hash family that certify this, and it's good enough for like a dictionary application. Okay. And we're gonna look more into dictionary today, and we're gonna just use this one today. But next class, you see that sometimes we need to use this one, and I introduce that next time. Okay, so just to recall, what we want to do is like to come up with a dictionary data structure that support insert and delete and check membership, right? And the model is that the keys are in some the key are from the universe of numbers. This number is big, but it's still a number, not just some arbitrary object. Okay. And we're gonna follow the same paradigm, come up with some algorithm that assume ideal hash function, and then see that okay, a simpler hash family still works. Last time we see this one. Okay. It has constant expected query and update time. And today we're going to see this. Okay. Let's start with the first one. One level perfect hashing. Okay. Just to recall the data structure from last time, it's just okay. You just have a element, a key, and then just choose a random cell according to your hash function, and then put it into the random cell. If there are more keys mapped to the same cell, then just put in the linked list. Okay. So that takes the expected length of the list here is constant, but it can be longer than constant. Now what we want from today is that we want it to be worst case constant, not just in expectation. Okay. So yeah, when m is n, expected time is constant. But if somehow I can guarantee that there is no collision, no keys, no two keys mapped to the same place, then I will be good, right? So we're gonna try to do that. And the idea is simple. So it's the same algorithm, except that I allocate more space. Last time I allocate only n cell. Now I allocate n square cell when there are like n elements. Okay. And this is now quite natural to think, okay, if you have more cell, then there are like a less chance to get collision. So that's the intuition, and we're just gonna analyze that indeed there shouldn't be any collision just by choosing the like allocate more cell to be n square. Okay, so let's try to analyze that there is no collision. So I said that distinct key x and y collide if this hash function map x and y to the same place, right? And if h is completely random, then the probability that x and y collide, which is this, is just at most 1/m. Okay. This would be true as well if h might not be a completely random function. If h is sampled from like a universal hash family, this is true as well. Just a defining property of universal hash family. Okay. So now let's prove that like the expected number of collision is going to be like even less than 1, like half. Okay. And how do you compute this? Well, let's say that let's say that this thing is just gonna be right sum x. One second. This thing is gonna be sum of x not equals to y, an indicator that x and y collide. Okay. And what should I do next? How do you analyze this?
You can.
Yeah.
You go, sorry.
I'll ask. You want to do like a. So you use linear of expectation, like you said there, and then you make like an indicator variable for the expectation of each. Like
Exactly.
X and Y pairwise.
Right. We just use linearity of expectation to move this in, and now it's just about analyzing one fixed x y. And then okay, let's do it. Maybe I just I prepared this anyway. So move this in, right? And now we analyze what is this. Expectation of indicator is just the probability that this event happened. So it's just probability that x and y collide. This is 1/m at most. Yeah. And what are like the number of distinct pairs of x and y is n choose 2, which is this part. But m is chosen to be n squared, so this is less than half. I just choose m to be big enough so that the expected number of collision is less than half. This should be at most. Okay, so once you have that the number of collision is less than half, then just by Markov, right? By Markov, you have that the probability that the number of collision is at least 1 is going to be at most number of collision over 1 when you've applied Markov. And that is almost half. So like the probability that there exists any collision at all is at most half. And okay, and also note that as I said, you see that this part I can just use universal hash family, like sample h from universal hash family instead of a complete random function, because the property that we need so far is just this thing. Okay, so in summary, the algorithm is like this. I just sample H with this range from a universal hash family. And then I try to insert all of my keys. Okay. And if there is no collision, then great, I'm done. If there is a collision, resample H again. Okay. And each of the time that I do this, like I know that with probability half, there's no collision and I would be done. So how many repetition, how many loop do I need to do in expectation? Like if I succeed with probability half, how many times should I need to retry in expectation? Okay, Scott?
2.
2. Yeah, why is that?
It's just, well, I think like the shorthand is just the inverse of the probability, but I think explicitly it's because of the geometric series or something.
Exactly. Like this is the probability that like something succeed with some probability p, and you ask how many times you need to repeat until you succeed. This is called geometric distribution, and the expectation of this number of this distribution is just 1 over p. Here, p is 1/2, so 1 over p is 2. Okay, so we just need to retry this like in expectation 2 times. So that's good, but you see that like the space is actually n squared instead of n, so that's not quite satisfying. But at least there's no collision, so the query time is going to be just constant. Good. Yeah. Any question? All right. So let's try to fix this. Okay. So we make some progress, but n squared is too big, not good. We want linear, right? Okay. So that's when we use 2-level hash family. And okay, so how do we deal with this? So in the first algorithm, when you get collision, you put in the link list. And the new idea is just that, okay, replace each list with the 1-level perfect hashing. Okay. That's the idea. Let's see how it goes. The algorithm is going to be like this. We're going to take the first level hash family, hash function, h. This is just the same as like a chaining algorithm. The first level is just like a hash function that map universe to range of n, not n squared. And then I'm going to compute this. Let Si be all the elements that goes to I, go to cell I. Like all these guys collide at I. And let's say that Si has size ni. Sometimes Si is empty, sometimes it's more than 1. When it's more than 1, that's when collision happens. But when collision happens, then what I want to do is this. I'm going to pick a random hash function again, hi. What's the range? It's from like U to, like from that map universe to range of ni over ni squared. Okay. And we're going to try to map Si into this range. Okay. And from last time, from like the 1-level hash function, perfect hashing, you know that like if you have ni guys and you try to map it using this, you don't expect to get collision. right? You might have collision with probability half, but you retry. So like I just keep retrying until you get that HI is collision free on SI. So think like this, and okay. And then HI, like append HI into array A. Okay. So let's see the example. Okay. So this is like a cell 0, cell 1, cell 2, cell n-1. Okay. n-1 is 0. So it gets 0 cell in this level 2 array. There is a level 1 array and level 2 array. Okay. This guy allocate just 0 cell on A. This guy, they have 3 elements, like S of, okay, maybe S of n minus 2 is this set, right? So this, like this 3, so this gonna allocate like a 3 square cell in the array, and then each of these gonna be mapped to some place in this range, and we're gonna map it so that there is no collision. If there is, then retry, okay. And do like keep doing this. Just keep doing this, like. Is the description clear?
Yeah. When you said retry, do you mean pick a new hash function?
Yeah.
Okay, and
Yeah.
so you're using still, like in this example, you still use the same array of length 9, but you're picking a new hash function.
Exactly.
From 3 to 9.
Exactly. Like just resample HI. Okay. So what's the time for lookup? If I want to look up, once I'm done with constructing this, what's the time to look up some like for like a whether like a key X is in our like a set
O1.
O1.
O1 to get to the right level, get to the second level, and O1 again within the second level.
Right. Yeah. It's just really like a lookup time is kind of just take 2 hash function evaluation. Right? So that's constant. And what's the space? The space is gonna be just n, because of here, like the first array is of size n, and the second array is of size ni square and sum over all I. Okay, and now what I'm gonna prove is that in expectation, this sum is just linear. If this is true, then we are done. Okay. So let's see why. So now we're just gonna compute the expected value of this. Okay. Okay, so we're gonna show this, that this is linear. Okay. So, okay, what's the number of collision, right? The number of collision is just gonna be, in total, sum over all I, and ni choose 2, right? If there are like 3 guys mapped to the same place, then the number of collision is like 3, like this pair, and this pair. If there are 4, then it's 4 choose 2. Okay. So sum over all I, and I choose 2. And now we can just say that so the expected number of collision is gonna be n choose 2 over m. Because for every pair of like there are like this is like every pair in the set S choose 2 choose two x and y that are not the same from our set, and the probability that x and y collide is 1 over m, and n over n choose two pairs. So this is just m choose 2 over m, right? And this is like basically n over 2 at most. Okay. So it means what? Oh, sorry. It means that, like, you see, like just combine this together. And this. So this is just the number of collision, but the expected number of collision is n. It's like at most n. So in expectation, this thing, this is just basically, like this is just basically ni square over 2. Like this is just this order. Okay. So it means that when you combine these two inequality, you get that indeed the sum of ni square is just On. Okay. So we are done. Oh. Question about this? Yeah.
So since it's only an expectation, do we technically have to like say that it's O of n space in expectation?
Good
or is
question.
it because we can like re-roll hash functions that it's actually like always going to be O n because we'll just like re-roll until we get.
Exactly. Very good question. I'm gonna talk about this actually, but let's talk about this now. Yeah. Now we have that the space in expectation is On. Let's say 10n, right? And like in expectation, but we would like to make worst case guarantee of the space. And okay, let's say this is exactly 10n. Now we can ask like how do we guarantee the space in worst case? And the answer is if in expectation the space is at most 10n, then the probability that the space is more than 20n is what?
So 1/2 using Markov's inequality.
Exactly. It's 1/2 just by Markov. So take this in like this should be like a kind of ingrained into your mind that okay, when you have expectation and you want to analyze like that, it is like kind of twice the expectation, then just apply Markov, like right. So this is just most expectation space over 20n. So this is the probability that something is more than, let's say, 10 times expectation is 1 over 10. And here is twice expectation, so that's 1/2. Just this Markov inequality should be like it's really intuitive, and you should always you should be really comfortable with this. Okay, so it means what? The probability that like this thing is more than, like the space is more than 20n is 1/2. So you can just, it means that if you try to build this hash function and until like if the space is more than 20n, just say that you fail and retry. How many times you need to retry? Now in expectation, you need to retry 2 times because this is again like a geometric distribution. Okay. So we have worst case lookup time. We have linear expected space, which we can make worst case. But we're not quite done yet. What is not like, why are we not done? Last thing we need to fix. This last thing we need to fix.
Got time or no?
The time is good now. The time lookup time is just two hash evaluation. Yeah,
We're still picking an ideal hash function.
exactly. We still use ideal hash function. So there's no way this is efficient. Right? And okay. So we're gonna try to use universal hash family instead, right? And I claim that it's okay to use it. And why is that? The reason is, okay, this is just like a one level perfect hashing. And we saw before that one level perfect hashing, you can just use universal hash family. What about this? Why was it okay to use, why is it okay to replace this with a universal hash family? Yeah.
I don't know if I'm gonna explain it well, but I think it's because we're evaluating, like when we do n choose 2, we're evaluating the number of collisions, and we're never evaluating, we're never doing any evaluation of more than two colliding with each other, basically.
Exactly.
So all of our logic is valid if we just replace it with universal.
Exactly. Very good. Thanks, John. Like, to see whether like it's okay to use universal hash family, like to sample from universal hash family or not. You just need to look into your analysis. And the only place that we use, like, we need to use only this reasoning to bound the number of the expected number of collision. We just need that. Probably that they collide, two things collide, is small. That's the only thing we need, like as a behavior of random function. So now just you see that this is what we need. So we just use universal hash family. We don't even need two wise independence. We just need that two things collide with like a small probability. Okay. Okay, so okay, we have this and this, and then two hash function evaluation now is gonna be just constant because universal hash family, like there exists the simple one that you saw that have small evaluation time. Okay, so we get this so far, and as I discussed, we don't need to pay expectation. Just reroll until it's linear. Okay, so far it's good. Like we get worst case space linear and query time constant, but it doesn't really support updates. Okay, why is that? The reason is that so you see, even for like a one level hash function, one level perfect hashing. Sorry. Okay. This one doesn't really support like insert a new element because our algorithm here is that okay, fix a set S, like set of element S, then we're gonna reroll until there is no collision. So if you now insert one new element, now there might be a collision, and it could be the case that for each insertion you might need to to reroll many times, like need to reroll after each insertion. So that's not a good way to deal with this. Similar to two-level hash function, like two-level perfect hashing, like the way that we construct A is that like we know that there are like let's say this one has 3 keys here, and then we would allocate 3 square cells in A. If there are more more guys here, we need to reallocate the whole new array here. So it's not convenient. Like there is a way to fix this, but it's not nice. On the other hand, the new one, Cuckoo hashing, is really nice and it's really practical, turns out. And I'm gonna tell you about this today. Yeah. So next one is Cuckoo hashing. Yeah.
Sorry, when it says expected amortized on the update time, is that different from just expected or just amortized?
Yeah. So it means that, yeah, it's both expected and amortized. Yeah. You'll see what it means soon. Yeah. Okay. But like, this is the one that are really old, and this is like newer, and it's just got like a Godel price or some price soon-ish. You see, it's a beautiful one. Like, okay. So now in Cuckoo hashing, let's say that I did not end by the number of keys. Okay. So now I allow both insertion and deletion of keys, but let's say at any time there are at most n keys. And again, I'm gonna start with an algorithm description that use ideal hash function. I'm gonna choose two functions, h1 and h2. And then I'm gonna allocate this many like a array of like a size m. M is 6n. Okay. And then for each key, okay, basically x will be allocated at first array at position hix, or second array at position h2x. Okay. And with picture, it's going to be clearer. So this is like a first array, second array. And I say this is a key f. Then key f will be either like, and this is like the place that this is h1 of f is 8, and h2 of f is 8. And f will either be stored in here or here. Similarly, like for C like h2 point to here, h1 point to here for C, h2 points to here, and now C is stored here. So when you want to look up, then you just need to look at 2 places and check if the element is there. Okay. Like, let's say maybe I want to look for like a Z, and Z point to this place and this place. And then I see that, okay, this place store E, so C is not there, but maybe it's here. So C is, but I look up and like there's no Z. So then like the Z is not in my memory. Okay. And to delete is simple as well. Just look up in both places and delete if it exists. But for insert, this is gonna be interesting. Okay. So I'm not gonna read this. Let me illustrate the idea by example. Okay. So suppose that like these keys are already in the table, and okay, like it's like each key is either in the place of A2 or in A1. And now let's say that I want to insert X, and the key of like let's say that like X, like H1 and H2 map X to 0, both of them. But if one of them is null, then this will be easy. I just okay. Then X just put X into the null cell, and we are good. But now like both A and B are allocated, so we cannot really like put X here. We need to do something. And the idea is to kick some guy out. Okay, so I'm just gonna choose like okay, let's kick A. Now A is out. Now A need to go somewhere, so A just gonna kick the next guy, and repeat. So A kick D out. D need to go somewhere. D has two choices. If it's not here, it need to go here. So it kicks C out. C need to kick E out. Now E can go to here. Doesn't need to kick anyone. And that's when we finish. Okay. So I'm just gonna keep looping like this until I'm done. You see what can go really wrong with this? Yeah.
There's a cycle.
Yeah, that can be like, actually a cycle itself could be fine, but it could still be the case that everyone just keep kicking everyone. What's your name again?
David.
David. Thanks, David. Yeah. So, yeah, there can be an infinite loop. And what we're gonna do is this. Let's say that I suppose that I loop for like a long time, keep kicking, and like let's say more than 2n times. Yeah. And I cannot finish. Then I know that I would be in the infinite loop because there are just like n keys. If I repeat this more than n times, then like there's an infinite loop. So the idea is okay, infinite loop. So my hash is not great. Let's rehash everything from scratch and restart. That's the idea. Okay. Yeah.
So why is it 2n times? Isn't n sufficient? Because there only could be n keys.
So good question. You're gonna see soon that like when we do this, in the worst case, you might need to look at each element 2 times. Yeah. You're gonna see the example soon. So, okay. So like this is also like kind of why the insertion time is in expectation amortized small. Because first of all, this is about randomized process. So we analyze expected time, and once in a while you're gonna need to rehash. Like once in a while you're gonna spend so much time, but most of the time you spend small time. So that's why it's amortized. So it's both expected amortized. We're gonna try to see that like insertion time here is really small in expectation and amortized. And the analysis is really not clear and like it's advanced. I'm gonna try to explain it to you. So we're gonna look at a graph. I call it Cuckoo graph, right? And the node here just gonna correspond to entry of array. Okay. And for each key x, right? X point to 2 place. Then I just create an edge between the two nodes here. So note that there are n here is the number of edge, not the number of nodes. Okay, there are n keys, so n edges, and the number of nodes is 12n because each side has 6n nodes. So this is a graph which is really sparse in a sense that most of the nodes has degree 0. Okay. You can think of this as like a random sparse graph, like where like you have 12n nodes, and each edge actually like kind of just choose things randomly, right? So it's like a random bipartite graph basically, where you add nodes, edges randomly, but there are just n edges out of 12n nodes. Okay. So when do we rehash? Okay. So suppose that I insert x, and let's say that I denote CCX to be a connected component of the edge EX. So suppose that like we call insert x, and I claim this. If the component of CCX has at most one cycle, it could have one cycle, but if it has at most one cycle, then we will not rehash. Okay. So let's see some like example. Do I have example? No. Okay. So let me draw it. Maybe something like this. Okay. And suppose that I insert x, and let's say, okay, maybe one second. Oh. Okay. Maybe A is here, B is here, C is here, D is here. Okay. Like there are 5 nodes and 5 edges. So maybe I draw it like this. A is here, B is here, C is here, D is here, E is here. So this is EA, this is EB, EC, ED. Maybe I choose F, yeah. This is EF. Okay. And maybe this is EX, maybe EY, and EZ. So Y is here, Z is here. Okay, good. And now let's say I insert this X. Okay. And let's say I wanna kick, like now I need to put X somewhere. Okay. So maybe X kick Y out, and then Y would kick Z out, and then C would go here. That's like a lucky direction. But maybe I choose to kick A out. Okay, so let's see what happened. So X is now here, but then it kicks A here, and then B would be here, right? And then C would be kicked here, and then D is here. And then D would kick F to here. Okay. Now A has to kick X to here again. So A is here, and now X is here, and then Y is here, and then C is here. Make sense? Okay. So like I might kind of go through this and then see some So you see like I look at A twice. I look at like A would be like look at twice. So that's why I talk about like if I look if I loop like more than 2n times, then I know that I cannot finish.
Sorry. So I get the edges are like non-directed, like they go both directions.
Yeah, no, there.
How does it know? Because the first time A went right from on E to A. How does it know to go left the next time?
Oh, because so EA is here.
Yeah.
So there are just two places that A
A
can be.
use that. Oh, I see.
A can be either here or here. If it's not here, it needs to go here.
I see.
And for the second time, A was here,
So it can
but
only
it's
go.
got kicked from F, so it needs to be here.
Okay. Thank you.
Just keep talking. Okay. On the other hand, if there are more than one cycle, you might get to infinite loop. And the idea is like, imagine that like you have this cycle too, right? So I kick like just look at the same example. I kick A out and A kick X back and X would kick something here and it would just keep doing this. So if there are two cycles, like not good. Okay. So the idea is to try to say that actually there is no this event cannot happen. Like or can happen with really small probability. So let's like the key lemma is this. I have that there are like the number of nodes is actually like 12n, right? Look at two nodes I and j. Okay. The probability that there exists like shortest path from I to j of length L, I claim that it's going to be small, exponentially small in L. Okay. I'm going to prove this later. Okay. But yeah.
This is with all edges having like weight 1.
Yeah. Every edge has weight 1. Yeah. Okay. But if this is true, then we're gonna try to, let's say if this is true, then we're gonna understand a lot of things from here. Okay. So first, like fix any node I and j. Okay. And let's say that like what is the probability that is connected? If it's connected, it means that there must exist some path from like there must exist some shortest path from I to j. But like the probability that there exists shortest path from I to j for any length L is kind of small. So let's try to analyze this. This is gonna be at most. This is like probability that exists L and like a distance I and j is L. Right. If it's connected, it must be some like the distance from I to j must be some L, not infinite. And then here I just use union bound, sum over L, probably that distance I and j is L. This is just at most what? Like this thing. Just from here. Okay. So now I sum over all like a sum over like a something exponentially like a geometric series, right? So it's gonna be like this is gonna be like at most 1/2R because yeah, sum of like 1/3 to the L when L start from 1 to even to infinite. This is at most like a 1/2. Okay. Good. And okay, and we can analyze more. For example, what's the size of the connected component? Well, it's gonna be, we can like sum over J and then indicator that I and J connected. Okay. In expectation. But let's use linearity of expectation. So but then here's just what's expectation of this? It's just this probability, right? And we sum over all nodes J. So it's just, there are R many nodes. So it's just R times this thing. R times 1/2. So at most 1/2. Okay. So we now know that, like, okay, look at any node I in this really sparse graph. The expected size of connected component is actually even less than 1. So and that makes sense. Like, it's a really sparse graph, and most of the node has expected size like should be 0, close to 0. Okay. Okay. So now, what about this? This is when just a, if it's in the cycle, it means what? It means that the exists L at least 1 such that distance from I to I, but it's like a non-empty shortest path. So like when this is more than 0, like it's like I asked what's like the shortest non-empty path from I to I. If there is a cycle, then like it means that the distance, there exists a non-empty path from I to I. And so, okay, maybe I say this. Exists non-empty path, some L at least 1, and exists non-empty path length L from I to I, Yes.
This is also under the assumption that we can't reuse edges, or because I feel like wouldn't I always technically be in a cycle because you can go from like I to J and then back to I since it's undirected.
Oh, here I mean really like a kind of you don't reuse edges. Because the cycle that we kind of care about is like a cycle that you don't actually you cannot just come here and here like you. Okay, but what is this thing? Now it's just like a use union bound, right? Union bound over J over L, and the probability that this thing, this thing, okay. But this probability is just at most this thing again. Right. I mean, I just copied this part to this. The probability that there exists non-empty path of length L from I to I is exponentially small in L by the key lemma. And so this is just the same calculation, and it's most it was 1 over 2r. And so the probability that there exists any cycle is what? Yeah, now you tell me. How would you analyze this?
I guess
I claim that this is at most 1/2. Why is that? John?
R again.
You go.
Wait, is R the number of nodes?
R is the number of nodes.
So the probability that there exists a cycle is less than or equal to the probability for each node, like summed using the union bound that they're in a cycle.
Exactly.
So that's just gonna be 1 over 2r times r, which is 1/2.
Exactly.
Less than or equal to 1. Yeah.
Good. Yeah, if there is a cycle, there must exist some I that is in the cycle, some node I. So we use union bound. Sum now just sum over all nodes. Look at the probability that that node is in the cycle. This is the probability of some fixed node is in the cycle is 1 over 2r. Now we sum over all nodes. So that's like a sum over all nodes. And now probability that I in cycle, that's r times 1 over 2r. Okay. Good. So now this is the probability that we want, basically. These two things. We don't even expect cycle. And like the size of each component is actually like small, less than half in expectation. Okay, so let's try to now, we kind of ready to analyze this. Okay, so after n insertion and r is large enough, okay, and we have this thing, okay, and we're gonna rehash if there exists. If we rehash, then we know that there must exist two cycles. In particular, there exists at least one cycle. But we don't even expect a cycle. Okay. So so if we rehash k times, then it means that like for each rehash there exists a cycle. But the probability that there exists a cycle is at most 1 over 2. So if we rehash k times, then that like this probability is just 1 over 2k to the k. So expected number of rehash is just then here, which is like a converge, because it's like each term decrease fast, so it's converged to a constant. Okay. So we're gonna rehash just basically constant time in expectation. So the insertion time that it takes is gonna be insertion time of x. We're gonna spend time at most is connected component size, and each connected component has size expectation constant, like even half. So we're gonna spend constant time in the expectation. So the total time that we're gonna spend, right, is like number of insertion times n, and like each insertion times 1 in expectation, and number of rehash times n. Okay. So in total it's basically linear when we have insert n many nodes, n many keys, sorry. So you see, like we compute total time, total expectation time. So it means that it means that we get like constant expected amortized time after n insertion. N insertion takes all n time, so it's constant amortized, but in expectation. Okay, so we are good. Assuming the key lemma. The key lemma, which is here, right? Let's try to prove the key lemma. Okay, so we're gonna prove by induction. Okay. So let's prove induction on L. When L is 1, it means that if the x is the shortest path from I to j of length 1, this just means that x is an edge from between I and j. So let's analyze what is the probability that the x is an edge from I to j. And that's simple. There is an edge from I to j if there is a key that map, like one side map to I and one side map to j. Okay. What's that probability? Like I, j it's just right. I use union bound here, right? H1 x map to I, H2 x map to j. Okay. What is this when Hi and H2 are just random? Not quite, not really. Like, what is the probability that this H1 map x to I, for example? What's this? 1 over what?
M.
1 over m. Yeah. This thing alone happened with 1 over m, right? M is basically like r over 2. There are two sides. Yeah. How about this event? Also 1 over m. And they are independent. Okay. So this is just basically 1 over m squared and sum over all x. So this is like sum over all key. So this is n. And so this is like 1 over r over 2 square, and r is chosen to be 12n. So this is, you can calculate this, and this is gonna be like 3r, like we need.
So are we still assuming right now that we're using a perfect
Yeah,
hashing function?
we assume that. Okay. So now next, let's look at the case when for general L, right? And then if the x is a path of length L, then for some k, basically for some k, this is I and j, there is a k, there is a path, shortest path from I to j of length L minus 1, and then this is an edge. Okay, so let's analyze this. Okay, so basically there are two events that happen at the same time. We want to analyze what is the probability that these two events happen. Now the first event happened with this probability by induction. How about a second event? Well, I'm gonna actually analyze this. Analyze the probability that second event happened, given that we know that the first event happened. Why? Because if we know this, then you know that the probability that these two events happen at the same time is just probability of the first event at times it's probability that the second event happened given the first event. It's just like equality. So I'm just gonna analyze each of these separately. The first event happened with this by induction, this probability. How about the second one? I claim that, what is this? This is just a probability that that there is an edge between j and k. Given that we know that there are many other edge outside, like many other edge are somewhere, given that there are a path from I to K. Okay. But I claim that this is going to be at most the probability that there is an edge, because these two events I claim they're kind of negatively correlated. The fact that we know that there are many other keys, like look at this again. J. Here is like just we know that there are many other keys that map somewhere else. Just reduce the probability that just reduce the likelihood that there is some key that map to this edge. So this is gonna be like at most this. Make sense? But the probability that there exists an edge from K to J is something that we have analyzed. So then just multiply them, like the probability that two things happen is just this, which is I R times R, and then you sum over all R guys, so you get this thing. So we are done. Okay. So you see that this is kind of not trivial analysis at all, but actually it gives you a really nice algorithm, but this is non-trivial even when we assume like ideal hash function. Okay. But it's really practical. But more on this cuckoo hashing. We can try to avoid cuckoo hashing, but I will not do this in class. It turns out that just using universal hash family is not enough at all. And the reason is that, like you see, we kind of use some analysis that is way more than just like our analysis use something way more than just saying that the collision probability is small. Yeah. So we use way more than the probability of universal hashing, and it turns out that like log n wise independence is enough, but log n wise independent is not so simple. Next class you're gonna see example of two wise independent. But anyway, like there are like some other simple hash family that works, and actually practical to implement. It's called simple tabulation. If you want to know, you can see. You can refine this a bit further. M could be set to be like not 6n, but like just a bit more than n. But the analysis is more complicated. Also, we can also say that we can just rehash when we loop more than log n times. We actually expect that there cannot be any component of size more than log n with high probability actually. Anyway, you can also turn the expected amortized time to be like to get amortized time with high probability as well. Like basically what I show you today is like a basic analysis of this really practical hash, like a dictionary based on cuckoo hashing. And yeah, any question about cuckoo hashing? Okay. So about cuckoo hashing, it's not like we are really done because we assume ideal hash function, but it's gonna come kind of beyond the scope of this class. Yeah. How to not use it. Okay. So I'm gonna repeat this again, that this is a really big open question. Can you get a dictionary with update and query time constant? It's a really cool question. Like such a basic data structure, we still don't know. Okay. And so next class, we're gonna talk about streaming algorithms, and you're gonna see more example application of like a pairwise pairwise independent hash families. Oh, 1 second. Yeah, I plan to give to prove you this, but you can have a look at home. It's just calculation, like why this family is really universal hash families. Okay. Okay. Let's finish early today, and yeah, see you next week.